Welcome back to this NPTEL online course, online certification course in molecular rearrangement and reactive intermediates. So I'm continuing with the organosilicon chemistry. In the last two classes, I talk about organosilicon chemistry, mostly the discovery of silicon and the different type of coordination number. You have seen up different type of the tetrahedral versus the trigonal bipyramidal structure. If it is pentavalent silicon, also I talk about some of the important effect like alpha effect and the beta effect. And also I think I also included one of the important reaction using organosilicon compound, which is Peterson olefination. I'm going to continue with Peterson olefination, and then also I'm going to include some of the other important reaction like the Brook rearrangement. This is a very important reaction using organosilicon chemistry. Then there is a cross coupling, so I'm going to talk about the Hiyama coupling, some silyl Heck coupling reaction, and my lecture will end with the Fleming-Tammany oxidation. I think that is another important reaction. So last class I talked about the Peterson olefination, and one of the things I think which I didn't go into the deeper. I think I talk about that the generation of the alpha silyl carbon ion from the beta from the alpha effect. So from the alpha effect, you can understand that it is going to get stabilized, this corresponding carbon ion, because there is a sigma star and this non-bonding interaction, correct? Because of the electron donation to the sigma star, that's why this carbon ion is stabilized. And then I talk about that once is add to this aldehyde, because this you can think about like some sort of a very similar to organolithium or Grignard you have seen, correct? This is a carbon with a negative charge which is going to add to the corresponding aldehyde. So it's hard, so it is going to go for 1,2 addition. After 1,2 addition, it is going to generate this corresponding beta hydroxysilane. So once you have this type of intermediate, now there is important things, because in the last class I only talk about the formation of beta hydroxysilane. You give acid, you give base. You can see that in case of acid we saw formation of the trans-selective olefin. If you give base, we have seen formation of the Z olefin or cis olefin. But the other important thing is, before we go into that, this is very important, that how this nucleophile is going to attack here, because here you can see once the nucleophile is going to attack, you are generating two chiral center here. If you see here you are generating two chiral center, so there is a possibility of diastereomers. Now it could be a trio or it could be a erythro. Okay. So now first, if you try to think about the attacking of nucleophile, okay, to the carbonyl compound, then one of the important thing is, if you try to see when the nucleophile is approaching there is two different things can happen. Once you have a R2 group, so there is three important group. One is R3, which is with the carbonyl. One is R2, which is attached with the CH2 and silicon, and another is the silicon. So if you see, based on the structure of these three, you can either able to get to erythro or you can able to get to trio. It can generate trio or erythro. Okay. So now the question is, once the nucleophile is attacking there, if the silicon is more bulky than R2, because what is going to happen when this is going to attack to this corresponding aldehyde, if the silicon is bigger in size, it is going to be try to be anti to this R3 of the aldehyde, because if R3 is a bigger group, silicon is a bigger group, they try to be as far as possible. So this is the position they want to be. Okay. So then what is going to happen? Then you can see there is the possibility that you can put silicon here, R3 here, which you try to draw, okay, in the different type of projection formula, and at the end you can see you are ending up forming a erythro compound. Once you quench with the water, the O minus will get the proton form the OH. So you end up getting this beta hydroxysilane, but it is a erythro. Okay. But if it is the R2 is more bulkier than silicon, if your R2, which is the one which attached after the silicon CH2 and R2, correct? So then the R2 will be try to approach such a way, because now if R2 is more bulky, then the R2 try to be opposite to the R3. Okay, because that will be the more stable conformation, where these two bulky group will be far from each other in the anti-conformation. In that case, you can end up after the quenching forming the trio. So in one case you can get to trio. So depending on the size of the silicon or the R2, which one is bulkier, you can get either trio or erythro. So that is a very important thing. And sometimes this is a problematic thing for Peterson olefination, because as if the reaction, the size are not really much different, then it will be difficult to control the formation of the ratio of 3O and erythro. In that case, from both cases you can able to get to the corresponding Z versus E olefin based on the next condition what you choose. Means if you use a acid or if you use a base from either of these 3 or erythro, you can end up getting to the E or Z olefin. Correct? So now if you have a mixture of erythro and 3O, then that is going to make the selectivity a big challenge. That's why a lot of time you see in that Peterson olefination was mostly used for formation of the terminal olefin, where you don't have to deal with E or Z. Correct? I think I already talked about this, that once you use a acid, it is going to form OH2 plus, and now the silicon can give electron density to the corresponding sigma star orbital from the sigma to the sigma star donation, and that is going to weaken this OH bond. So that's why there will be so you can write this mechanism like that, so that can weaken also carbon silicon bond. So there will be anti-elimination to form the corresponding trans product. In case of base, what is going to happen? In case of base, we know that is generally we are not going to end up to the corresponding silanol. There will be this O minus after the addition to the aldehyde. The O minus can attach with the silicon from the same site. Okay, formation of the corresponding carbon ion, and then formation of the double bond. So that will end up forming the cis. So this reaction is stereospecific. So this was not a problem. The problem is the generation of 3 or erythro. Okay, I think you guys understand this particular problem in the Peterson olefination. So now you can see once you started with a particular diastereomer, either you started with the 3O or from the erythro. Now I think once you put it acid, you can end up getting from this one, you can end up getting to the corresponding E product, and from the CO you can end up getting the corresponding Z product. Again, I think I already talked about this mechanism before. Okay. So here I think in these cases also you can see the mechanism will be both cases similar, because we treat with the corresponding acid. Again, if you treat with the base, of course you will end up giving opposite selectivity. Means here in case of where you are getting a E, you end up getting a Z, where you are getting a Z, you end up getting a E. Okay. So that's why you can see Peterson olefination is particularly used for synthesis of exocyclic double bonds. So when you are thinking about synthesis some sort of a terminal olefin, okay, or you can think about something like some sort of exocyclic double bond like this. Again, there is an example given here in this reaction. This is corresponding Grignard going to attack to the, so you can see here there is a possibility of 1,4 versus 1,2, but this is a hard reagent, corresponding Grignard going to go for a 1,2 addition here, okay, first, and then after the elimination of water, it is forming this exocyclic olefin. So that's I think that's all about the Peterson olefination. We are moving to another important reaction called Brooke rearrangement. It was discovered by Canadian chemist Professor Adrian Gibbs Brooke in the 1950s. So it's a migration of silyl group from carbon to the silicon under basic condition. Or if you have a aldehyde, or if you have a the acylsilane, you add a nucleophile to the carbonyl, that will generate this some sort of a O minus species that can also participate in a Brooke rearrangement, which we are going to discuss in a minute. Okay. Or if you have something like 1,2 or 1,3 silicon and OH, then if you treat with base, it can generate the O minus that can also participate in the some sort of a migration of the silyl group from the carbon to the oxygen. So formation of silicon oxygen bond, that is a very important. I think I talked about at the beginning about the bond bond energy, and you have seen that the two important thing about silicon is silicon fluoride bonds and the silicon oxygen bond, correct? So because these bonds going to be stable, so this is the driving force. And then sometime you can see there are retro Brooke rearrangement. We are going to discuss some of this. The important thing is migration occurs with the retention of configuration in the silicon center. So the migration occurs with the retention of configuration, which I am going to explain also in the during the mechanism. So there are a couple of different things which you put by n. N could be 0, that means this both the, so both are in the same carbon. That means we are talking about formation of O minus, and the silicon are in the same carbon. Okay. In that case also what is going to happen? It is going to take the silicon and then form the corresponding. So you end up generating a carbon ion here with a O silicon R3. So this is called Brook rearrangement. Okay. You can see here now, if you have this acylsilane, and now if you take a nucleophile and add it to the acylsilane, if you have corresponding organolithium, Wigner, and other nucleophile, once you are attacking with the carbonyl group, you are generating this O minus here. Now that can now take, react with this, that can take the silicon from here, and once it is giving electron density to the silicon, what is going to happen? It is going to form this pentacoordinated silicon intermediate. We talk about that in the silicon chemistry, that the carbon which do not have a d orbital cannot form this pentacoordinate, but silicon does. That is the important thing here, because once this pentacoordinate species forming happening, now then there will be a 1-2 shift. There will be 1-2 shift of silicon moving from carbon to oxygen and generating a carbon ion in the carbon. Now that carbon ion can be trapped with a proton to include H, it can trap with the electrophile and more. Okay. There is an example for this Brook rearrangement here. Here you can see both CHO and these are in the ortho position and the silicon, and so this is again a chromium arine complex here. So now once this enolate is attacking to the aldehyde, it is forming this O minus lithium, which now have a 1,4 silyl migration. So now you can see this is a 1,4 Brook rearrangement happening to generate this corresponding lithium in this carbon, because the silicon, so the O minus is forming this pentacoordinated species, leaving, once it is forming pentacoordinated species, it is actually giving electron density, that is, it is weakening this carbon silicon bond to generate this corresponding carbon ion here, and then that can able to do further intramolecular cyclization to form this compound, which was converted to the important natural product. So now we can talk about a 1-2 Brook rearrangement. In these cases here, what is happening? First, the methyl lithium is attacking here. You can see methyl lithium is attacking here, formation of the O minus, and the silicon going to transfer from the carbon to the oxygen, formation of this carbon ion going to happen first. Okay, and you end up forming OSIMe3 and then methyl and then this minus, which can participate, get into the SPH group to generate the olefin here with a 97:3 E versus G selectivity. Okay. Then there is 1,3 Brook rearrangement here. Here what is happening? Once you have a beta keto silane, so this is, you have this alpha keto, this is a beta keto. So once you have this beta keto, what is happening? Then this can, if you heat up, then there is a rearrangement happening, thermal rearrangement happening to generate this silyl enol ether. Okay. So which can react with the corresponding electrophile. Okay. You can see another example here. Instead of this thermal rearrangement, instead of carbonyl, you have alcohol here. If you treat it with terbutoxide, that can abstract this proton from this OH to generate the O minus, which is now again going to give electron density, going to interact with the silicon to form this pentacoordinated species, because silicon has the vacant d orbital. Now that is going to weaken this carbon silicon bond to generate this corresponding carbon ion here. Okay, which can be treated, take a H plus to form the corresponding product. 1,4, so there is an example of 1,4 Brook rearrangement. You can see this particular compound, carbon with silicon and sulfur, 2 sulfur and a lithium, which can add to the corresponding the less hinder position of the epoxide, open the epoxide, generate this O minus here, again which can, you can see now it can participate in the 1,4 Brook rearrangement. It can give electron density to the silicon d orbital, formation of the pentacoordinated species. Then you can see this bond is getting cleaved from this corresponding carbon ion here, which can now attack, now it can ready for some sort of SN2 reaction here, because this is a carbon ion, again you can see, which is a stabilized carbon ion with 2 sulfur group next to it, okay, which can participate in the SN2 reaction to get to this product. There could be a retro Brook rearrangement can happen, not only the Brook rearrangement, after that also there could be something called retro Brook. Here first you have this oxygen or sulfur here. This can go for a directed lithiation. We have learned this in organolithium chemistry, that there will be directed lithiation here to generate this organolithium, which can now react with the silicon to cleave the oxygen and silicon bond to generate a OH, which now can go for treat with any n-butyl lithium for another type of directed lithiation from here through this groove, and then you can treat with the electrophile. When you will treat with the sodium hydride and DMF, again there will be the O minus can go for another retro Brook, the O minus can come and take the silicon here. So this is the retro Brook rearrangement, because you can see here what is going to happen. So here there is not a retro Brook, there is a 1,4 Brook. First there is a retro Brook happening here, because this is getting cleaved the oxygen silicon bond, and here there is a Brook rearrangement happening. The O minus is taking the silicon and formation of this minus, which can take H plus to get to the corresponding product. So in this reaction, what we have seen first there is a retro Brook and then there is a Brook rearrangement. Okay. There is a radical Brook rearrangement. So you can see if you have this, as I was mentioning, this acylsilane species, then if you can generate the radical from acylsilane under H nu, then that radical can add to this alpha beta unsaturated compounds. Once the radical going to add here, what you are seeing here, that is generating this radical next to the ester, and you have oxygen in radical here. Now once you have oxygen radical, it can participate in 1,2 migration. Okay, it can interact with the silicon, then cleavage of this carbon silicon bond to generate a radical. Both the radical can recombine to form this corresponding cyclopropane. Okay. There is another example of radical Brook rearrangement here. You have this acylsilane and you have this corresponding halide. Now if you treat with tributyl tin hydride, AIBN, we have already discussed in the radical chemistry that will generate this corresponding tin radical. So the tin radical can allow the homolytic cleavage of this carbon hydrogen bond to generate the radical here. Now if you have this radical, it can add to this carbon, to the acylsilane to generate this species, which can participate in 1,2 shift to generate this radical on the carbon, which can go for a hydrogen atom abstraction, like a hydrogen atom transfer from tributyl tin hydride. So hydrogen atom transfer going to happen to get to the corresponding product. Another example here, first formation of this radical from this formation of this tin radical can allow generation of the cleavage of this carbon bromine bond to generate the radical species, which can add to this corresponding acylsilane. Then generation of there is 1,2 shift generation of this carbon radical, which can go for 5-exo trig cyclization, and then finally hydrogen atom transfer going to happen to form the corresponding product. So we have learned about the radical Brook. Now it's called Aja Brook. So it is not only that always there will be oxygen. If there is a nitrogen, particularly for this type of compound where the carbon having a some sort of a amine at the same time having a silicon. Now if you treat with the n-butyl lithium, first thing is this is the acidic proton going to be abstracted to generate this n-lithium, which can participate in 1,2 Brook rearrangement to generate this carbon ion here. Okay, which can finally going to trap the methyl iodide, because this is a allyl carbon ion going to form this corresponding vinyl amine. There is another example about this dithion compounds. If you have a silicon group here, then if you treat n-butyl lithium, then this is the proton going to be abstracted to generate the corresponding carbon ion here. If you treat with the corresponding RCN, it is going to add to the CN to generate this N minus and lithium plus, which can participate in 1,3 as a Brook rearrangement. You can see formation of this pentacoordinated species going to happen. Then cleavage of this bond, generation of the corresponding organolithium here, which can be trapped with the electrophile. Okay. So we talk about the Brook rearrangement, and again I think there will be some of the problems will be given in the assignment, which can practice you more for the final exam. I am going to talk another important reaction called Hiyama coupling. So we have learned about a lot of the cross coupling in this particular course. You have learned the Suzui coupling, Nigisi coupling, Kumata coupling, Sonogashira reaction. Here you are going to see about the Hiyama coupling. So here you can see this reaction is a coupling between a cross coupling reaction between organosilanes with the organic halide or triplet. So you need a organic halide or triplet for the oxidative addition. We have learned previously, correct? Once you have a palladium 0, you can, if you have a aryl halide, it can participate in the oxidative addition, aryl halide or vinyl halide. And then the thing is, there is a next step where you will see the important step, which is I am telling you again and again, is the transmetallation. At that step, if you use a boron, then that becomes a Sujui coupling. If you have a organozinc, that becomes a Nigesi coupling. If you have a Grignard, become a Kumade coupling. And if you have a silicon species, that become a Hiyama coupling. Okay. Sometimes this is also called the Hiyama-Denmark coupling as well. So you can see, I think we're going to discuss the mechanism of this reaction, and then generally the organosilicon is activated using fluoride or hydroxide to form the pentavalent silicon. So that is, I think we're going to come to that point where you have seen for Sujui coupling also we need to use the base to form the boronate species. Here also you have to make a pentavalent silicon species to activate this organosilicon using F minus or a OH minus, which can generate this type of the pentavalent silicon species, which can allow the transmetallation step to take place. Because the oxidative addition will going to take place, we have already learned about this. The important step is this one, where you can use a F minus source which can attack on the silicon to generate this pentavalent species that will allow the transmetallation of this R1 group from silicon to the corresponding palladium. So once the transmetallation happens, then the next step is the reactive elimination to giving to the corresponding cross coupling product and getting back to the catalyst in the reaction cycle. So there is a reaction here that you have this vinyl TMS and you have this corresponding iodide, the alpha naphthyl iodide. So that is going to participate in the Hiyama coupling. Again, you have to use some sort of a fluoride source here, which can allow this transmetallation step to happen to get to the corresponding product. Of course, if you want to do the same reaction, you can also use a Sujui coupling. In that case, you have to use a corresponding vinyl BPA. Other reaction here, you can see again there is a aryl bromide here with this corresponding the corresponding also there is 2 fluorine in this compound. Now, if you use a palladium source and then you use a NaOH, which can be activating the corresponding silicon for forming the pentavalent one for the transmetallation, then you can able to form the biaryl from there also. Okay. So it is very similar, I think, to the Suzuki or the Nigesi, but only thing is the other precursor here is organosilicon. Then there is silyl Hake coupling. So we have learned about, I think we have not talked about the Hake coupling here, which happen if you have this olefin and if you have aryl halide. Okay, ARI, and if you use this palladium catalyst and ligand and solvent, you can end up forming this type of compound here. So that is going to be the Hake, but the difference here is we are talking about silyl Hake. That means one compound will be R3SiX or R3SiOTF. If you have this thing, then that can also participate in the Hake coupling with the olefin. With the some sort of a styrene or some sort of a olefin. If you have seen about the Hake coupling, here the only difference is this type of silyl reagent was used. It can be done with the palladium or nickel to get to the corresponding the vinyl silicon compound. Again, you can see this is a very good method for the synthesis of vinyl silyl, and the cross coupling of styrene derivative with the silyl halide or silyl triplet is called the silyl Hake. Okay. Again, this silyl triplet failed to participate in the palladium catalyzed silyl Hake reaction without iodide additives. Okay, the strong silicon oxygen bond prevent the oxidative addition of silyl triplet. And generally, bulky phosphine ligands are optional for this reaction. Okay. So we are going to move further and going to talk about I think the last important reaction for this particular talk here. I think that that is the Fleming-Tamau oxidation. So that is a oxidation reaction. I think we have heard about that. If you have a carbon boron bond, you can convert the carbon boron bond to the OH. You have learned about the hydroboration oxidation discovered by Professor Brown, correct? Now we are talking about if you have a carbon silicon bond, how you convert the carbon silicon bond to the carbon oxygen bond. How do you do that? For that, Professor Tamau and Professor Ian Fleming, they have discovered a oxidation protocol called a Fleming-Tamau oxidation. So this is the protocol which was developed by Tamau, H2O2 KHF2 DMF room temperature 60 degrees, and Fleming condition HBF4 diethyl ether with MCPBA triethylamine and diethyl ether again. So again, you can see this is oxidation reaction. So, and the other important thing is we have drawn here a particular stereochemistry just to show you that in this reaction you will be expecting the reaction going to be stereospecific with retention of the configuration. Okay, that is very important. There is a retention of configuration. So you are going to see the stereochemistry retained. So you see the silicon was down here kind of, and then you can see also the OH is forming also from the same side. So there is a retention of configuration happening here. So first we are going to talk about the Tama process. Tama oxidation, at least one group on silicon must be heteroatom or hydrogen. That is one important criteria. Okay, we are going to come back to the mechanism also, you understand from there. And the rate of oxidation decreases with increase in the steric bulk on the silicon atom. You are going to learn in a minute that you have to use some sort of F minus for this oxidation to take place. That is why as the increase of the steric bulk increase, we talk about I think the protecting group as I think silicon as a protecting group for alcohol. If you remember, we talked that if the silicon have a bulkier group around silicon, then the deep protection become difficult because approaching of the fluoride minus become difficult. So very similar, if the Tama process need a fluoride minus to be attacked, then if your silicon getting a bulkier group there around it, then the oxidation rate will be much slower. Okay. Again, the Tama oxidation can be carried out with variety of pH and H2O2 and the oxidant. Okay. You can see it can be, and MCPBA is also commonly employed as oxidant here. Under acidic condition, you can use 30% H2O2 acetic anhydride KHF2 to get to the alcohol. You can use the neutral condition again in place of DMF, 30% H2O2 and the KHF2, or under basic condition also it can give to the corresponding alcohol. So now we are going to learn about the mechanism, what type of mechanism happening in this Tama process. So as I mentioned, once you are using a F minus source, this F minus is going to attack to the silicon to form this pentavalent species. But you have to understand, once you put a F minus into that, this become also very electrophilic, this species. So now if you have this type of nucleophilic H2O2 is there, then these oxygens are very nucleophilic, they can attack to the silicon to form this. Now you have you have the 6 different groups here, like 6 groups attached. From pentavalent it went to the hexavalent. Okay, hexavalent silicon species here, which can now take part in a 1,2 migration, very similar to, if you remember, in case of boron. Because now this R group can migrate from silicon to oxygen, and the OH can get out from here, because this oxygen bond in the peroxide are the most weak bond. So that will allow the cleavage of this bond to form this species here, which under workup, if you do the the workup of the reaction, this will end up giving to the corresponding alcohol. Okay. Again, you can think about that if you from this species, because if you again do the workup, that can attack the nucleophile in the silicon and get rid of this particular alcohol out from the silicon. Then I am going to talk about that, depending on the condition, like, so we talk about the the acidic condition, neutral condition, correct, but mostly I talk about once you have a alkyl silane, means it is the silicon which attached with a carbon which is sp3. Now we are talking about silicon attached with a carbon which is sp2. That means we are talking about this vinyl silane. Now if you have a vinyl silane, under neutral or basic condition, what you are going to end up, that once you have a silicon will be OH, that can be, so that will be enol, which can be converted to the corresponding aldehyde. But if you have a acidic condition, what is happening in acidic condition, it will not going to stop there, it is going to continue oxidizing to the corresponding carboxylic acid. And if you have a acidic, neutral or basic condition, if you have this scenario, of course, this can be converted to aldehyde, means I can understand if you have a R2 group here, you can clearly see that what is going to happen here, man, it is going to convert this to corresponding OH and R2, correct. That means what is going, this is going to convert to the corresponding ketone. Because of presence of the R2, it will be ketone. If R2 equal to H, then it will be aldehyde, which I shown here. In the Fleming process, as I mentioned, it could be a it could be a two-pot sequence, HBF4 first, HBF4 then BF3 with 2 acetic acid or then MCPBA, or it could be a one-pot variation which they have later developed with mercury acetate and acetic acid with the acetic acid, and then this peroxide species here, acetyl peroxide species here, or it could be the bromine, or it could be the KBr with this peroxide. Okay, that can also convert this corresponding RSI to the ROH. So we try to understand the mechanism of this reaction. If you have this corresponding the sealant species, if you treat with the H plus BF4 minus or HBF4, then there is a ipso. So we have learned about the ipso substitution, if you remember. At the beginning we talk about that once you go for ipso substitution, you will be generating a carbocation here which is in the beta position, and according to the beta effect, the beta carbocation will be stabilized because of the electron donation from this carbon silicon sigma bond. So we have learned after the formation of the carbocation what is going to happen. This is going to weaken the carbon silicon bond as well. So if you have a F minus attacking on the silicon, that can able to form the double bond here, okay, to get give you the silicon compound out from the phenyl ring. And now if you have this H2O2, that can attack on the silicon to form this pentavalent species. Now from the pentavalent species also it can participate in this 1,2 migration from the silicon to the oxygen. Okay, after the 1,2 migration, it can go for a hydrolysis to get to the corresponding alcohol. As I mentioned very similarly from the last mechanism also, Tamao cases you have seen, from this intermediate it can go for hydrolysis because water can attack here, and it can give to the corresponding alcohol and form this the silicon methyl OH and F, that can two of this species can form this particular ether. Okay. The retention of stereochemistry, I think I mentioned at the beginning that in this reaction there will be retention of stereochemistry on this Tamao or the Fleming oxidation. You can see if you start with 100% XO isomer, under the standard condition you end up getting 100% XO isomer. So you can see the XO isomer will give the XO product. Very similarly, if you have an endo isomer, it will going to give you the endo product. Another synthetic application, there is a I think this Tamao and the Fleming oxidation was applied in the natural pot synthesis. One of the example was the synthesis of pramans, I think it's a pramanicin. Yeah, it's a pramanicin. So the pramanicin natural pot was synthesized, and one of the important step here where they have converted this carbon silicon bond to carbon oxygen bond using this MCPBA KHF2. So you are seeing that this neutral Tamao oxidation condition was useful for the total synthesis of natural products. So in this particular class I talk about Peterson olefination, some of the things which I didn't talk about in the last class. Of course I talk about Brook rearrangement, several different variation, radical Brook, then Aza-Brook rearrangement, the Hiyama coupling, the Seryl-Heck coupling, and I end up with the Fleming Tamao oxidation. Again, here are some of the references, and again thank you so much for coming to the class. I am going to see you guys in the next class. Thank you.